Right, well, hello everybody. So today we're going to continue with our discussion that deals with ideal gas mixtures. Please keep in mind that previously we've looked at various equations that allow us to turn mixture properties into essentially properties that are equivalent to having a single component. So we could find, for instance, the apparent molar mass, we could find the apparent gas constant. What I'm going to do is I'm just going to continue with some example problems, and these will be different than the ones we've seen previously, but still they're to illustrate the use of these various relationships that we've already covered. So most of today's lecture is really just going to deal with examples. Now, the first example problem is as follows. Let's say that we have a gas mixture, and this mixture is at a particular temperature and pressure. So let's say that it's at 300 Kelvin as our temperature and 200 kilopascals as the pressure, and it basically consists of 1 kilogram of carbon dioxide gas and 3 kilograms of methane. Okay. What we want to find is the partial pressure of each gas, and we'd also like to find the apparent molar mass of the mixture, and we'd also like to find the volume of the mixture. Okay, so this is just a statement of the particular problem. Now, let's keep in mind that when we talk about partial pressures, the partial pressure is not going to be the same as the 200 kilopascals pressure of the entire mixture, right? Each partial pressure is calculated as if each component occupies the entire volume. So with that in mind, the partial pressures would be a fraction of the total pressure, although they would add up to the total pressure of this particular mixture. So when we do a problem like this, let's keep in mind that the partial pressures are going to be found using the mole fractions. So if we have component I, then the partial pressure of component I is just going to be the mole fraction of that particular component multiplied by the pressure of the entire mixture. So the first thing we really need to do then is simply find these mole fractions. Now, we have mass information. We're given that the mass of the carbon dioxide component is 1 kilogram. We're also given that the mass of the methane is 3 kilograms. And hopefully we remember that by simply dividing the mass by the molar mass, that's going to convert our mass data into molar data. So we are going to have to go into our property tables, basically table A1, and find some molar mass data. So the molar mass of the carbon dioxide is listed as 44.0, and this is going to be in kilograms per kilomole. And then the molar mass of the methane is likewise found in the same table at 16.0 kilograms per kilomole. So all we really need to do at this point is divide the mass into the molar mass, and that's going to give you the number of moles. So the number of moles of the carbon dioxide is then simply mass over molar mass. So here we have 1 kilogram over 44.0 kilograms per kilomole, and that gives me 0.0227 kilomoles. And then similarly, we're going to look at the methane, and we'll find the number of moles of the methane gas. Again, it's just the mass over the number of moles, the mass over the molar mass. So here, this is just going to be 3 kilograms over 16 kilograms per kilomole, and that's going to give us 0.1875 kilomoles. Well, now that we have the number of moles of each of the two components, we can find the molar mass of the mixture just by adding together the number of moles of each component. So we add the two numbers above, and we're going to get 0.2102. That's the total number of kilomoles for the mixture. Remember, the subscript m refers to the mixture itself. And now we can find the mole fractions. So the mole fractions, well, are just going to be n over n of the mixture. So for carbon dioxide, well, we're just going to take the ratio of the numbers that are shown above, and that's going to give me 0.108. And then similarly for the methane, well, again, it's just the number of moles of the methane divided by that of the mixture, and that's going to give me 0.892. So these are our mole fractions. Now, quite frankly, we know that the combined mole fractions of each component is going to equal 1. So I could have found the number of moles of the methane simply by subtracting the number of moles of the carbon dioxide from 1. But sometimes we can't do that. I mean, sometimes we'll have 3 or 4 or 5 components in our mixture. So using this methodology is really more appropriate. Once we have the mole fraction data, our next step is to find the partial pressures. So as was stated at the beginning of the problem, it's just going to be the mole fraction times the pressure of the mixture. So for the carbon dioxide, we have 0.108 multiplied by 200 kilopascals. So that's going to give me 21.6 kilopascals. And then the partial pressure of the methane, found likewise, 0.892 times 200 kilopascals. And that's just going to give me 178.4 kilopascals. Again, you could have just subtracted the partial pressure of the carbon dioxide from the mixture pressure of 200, and that would give you the partial pressure of the methane, but we want to use this method just in case we have other problems that require, the use of multiple gases. Now, we're also trying to find the apparent molar mass, so if this mixture was treated as if it were a single component, well, then we would have the following. So here now we would find the molar mass of the mixture simply by dividing the number of units of mass of the mixture divided by the number of moles of the mixture. Well, so here it's pretty obvious, right? We had a combined mass of 1 plus 3 kilograms. The combined number of moles was 0.2102. So if you just divide that into 4, we get 19.03. And that's the molar mass. The units are kilograms per kilomole. Okay. And then lastly, if we want to find the volume of this particular mixture, well, we would just use the ideal gas relationship that applies to this mixture. So we have the number of moles multiplied by the universal gas constant, multiplied by the temperature of the mixture, and then divided by the pressure of the mixture. So we would just have to multiply all these various numbers above together. We have 0.2102 kilomoles. The universal gas constant, we find that in the inside back cover of your textbook. That's 8.314 kilojoules per kilogram per kilomole per Kelvin. And the temperature of the mixture is given as 300 Kelvin. Please remember that if you're given temperature in Celsius, or if it's in the British units and you have it in Fahrenheit, you have to convert to the appropriate absolute temperature scale. So here, of course, we're using Kelvin. And then we just divide that by the pressure of the mixture, which is 200 kilopascals. Okay. Now, if you look at the units here, I don't see meters cubed anywhere, so you may wonder if we're really doing this the right way. But just remember that all the units work out just fine. I mean, a kilonewton per square meter is the same thing as a kilopascal. A kilojoule is the same thing as a kilonewton meter. Now you can see that all the units throughout are going to cancel. The only thing we're going to be left with are meters cubed. So we finish the problem, we do our math, and we get 2.62 cubic meters. And there is an example problem that illustrates the use of this material. So normally I would ask for questions, but I can't because this is an empty room. This is a makeup lecture recording. So I'm going to move on. All right, so now there's actually another example problem that I would like to do. And this example problem is actually from your textbook, from the 8th edition of the textbook. This is problem 13-32. So let me pull it up over here on the computer. Okay. So as you're reading this particular problem, let me read it along with you. This tells us that we have a rigid tank and that it contains 2 kilograms of nitrogen at 25 Celsius, 550 kilopascal, and it's connected to a different rigid tank that contains 4 kilograms of oxygen at 25 Celsius and 150 kilopascals. The valve that connects the 2 tanks is open, the 2 gases are allowed to mix together, and they reach a final equilibrium temperature of 25 degrees Celsius, and we're trying to determine the volume of each tank and the pressure of the mixture at the end of this process. In other words, the final mixture pressure. Okay. So you can't just look at the 2 pressures and assume that the final pressure is going to be the average of the 2. I mean, that makes no sense. We've got a different mass associated with each of the 2 components, and as such, you can't just do an average pressure. We're going to have to find this by looking at our mixture. We'll have to understand that the pressure of the mixture is going to be found using the same ideal gas relationship that we utilized in the previous problem. So number of moles of the mixture times universal gas constant times the temperature of the mixture, and then divided by the volume of the mixture. So this is the equation that we're going to have to utilize here. Now, in this particular problem, we don't appear to have enough data. I mean, we know the mixture volume, but we don't know anything about the number of moles. All we're given is information about mass, temperature, and pressure. But let's keep in mind that each gas, before mixture takes place, is still an ideal gas. We can very easily use the same ideal gas relationship, but not for the mixture, for each component. We'll find the volume of each component, and this would be before mixing. And again, using the same ideal gas relationship, it's just going to be, well, actually, it's not quite the same ideal gas relationship. We have mass data, so let's use the other one, mass times the gas constant R, which is specific to that particular gas, and then multiplied by the temperature of that gas, and then divided by its pressure. So for each gas I, we're going to use its own mass, its own gas constant, its own temperature, its own pressure. And this is data that we have, right? The gas constant we can look up in table A1, the temperature, pressure, and mass data we've been given. So we can find the volume of each component before mixing. We would then note that the volume of the mixture is just going to be the sum of the volume of each component. After all, the volume doesn't change just because we've opened up a valve between them. Once we have that volume data, then we can use that above to find the pressure of the mixture. However, still, we don't have any data on the number of moles, but that's easy, right? We know the mass, we know the molar mass. We can just divide mass into molar mass and find the number of moles. So we can find the mole number pretty easily for the mixture. We can find temperature, it's given, R. We can solve this problem pretty easily. So let's just go ahead and solve it then. So first, why don't we find the volume of each of the 2 components. We'll start with the nitrogen. So again, it's MRT over P. We have 2 kilograms of mass of nitrogen. We can look up the gas constant, and that's 0.2968. And this is now in kilojoules per kilogram per Kelvin. The temperature is not given in Kelvin, but we'll have to add 273 to that. So 273 plus 25 is the appropriate temperature in Kelvin. And we divide this by the given pressure of 550 kilopascal. And we go through our mathematics, and we end up with 0.322 cubic meters. Now, note again that there appears to be this unit discrepancy, but there is no unit discrepancy. We use the same identities here as we did in the previous problem. Again, noting that a kilonewton per square meter is a kilopascal, a kilonewton meter is a kilojoule, and you end up with the right units of cubic meters. We'll do exactly the same, find the volume of the oxygen. So here we have 4 kilograms. The gas constant for oxygen is, of course, different than that for nitrogen. It's 0.2598 kilojoules per kilogram per Kelvin. Again, this comes from table A1. We can then multiply by the temperature. It has exactly the same temperature. 25 plus 273 is 298 Kelvin. And then we're given the initial pressure of 150 kilopascals. Apply the math, and we get 2.065 cubic meters. Now we can find the mixture volume as just the sum of the above two numbers. And this mixture volume then becomes 2.386 cubic meters, and this is what we're going to have to use eventually to find, well, the pressure of the mixture. Now, as we move on with this problem, the next step would be to find the number of moles. So the number of moles of oxygen is the mass over the molar mass of the oxygen. So again, just take the numbers from the problem statement. I started with oxygen now, so we have 4 kilograms of oxygen, and then 32.0 kilograms per kilomole is the molar mass, again from table A1. So we can go through our mathematics here, and we end up with 0.125 kilomoles. And then similarly for the nitrogen, which is the mass over the molar mass. So 2 kilograms over 28.0 kilograms per kilomole. And that's just going to give me 0.07143 kilomoles. And now we have the number of moles of each component. We can now tie all this together. The number of moles of the mixture is just the sum of the moles of each component. And mathematically, this now becomes 0.1964 kilomoles. And last but not least, we go back up to our equation for pressure. So N times R universal times T over V. Again, all this data is for the mixture, except the gas constant, it's universal. So just plug in all the numbers we have, 0.1964 kilomoles. The gas constant is 8.314 kilojoules per kilogram, per kilomole per Kelvin. The temperature of the mixture is 298 Kelvin again, that was given. The volume of the mixture we found above is 2.386. So we go through our mathematics, and we find that the pressure is 204 kilopascal. So there is another example problem. Okay. Now, pardon me. One thing that we have to understand is that we're not just finding these various thermodynamic properties because it's interesting or fun. I mean, it may be, but ultimately we're going to use this data to solve problems that involve the first law of thermodynamics. If we're solving a first law problem, we're going to need information on masses, mass fractions, apparent molar masses. We're going to need information on properties that we've not yet talked about in the context of mixtures, internal energies, enthalpies. Eventually we're going to require entropy calculations. So we have to think of this data or this information, these problem-solving techniques, in terms of the kind of problems that we're going to look at. And frankly, the problems that we're going to look at are the same kind of problems that we've already seen. They're first law problems, either for closed or open systems. So what I would like to do is talk a little bit more now about the properties of ideal gas mixtures. Now, it's not difficult, but we do have to understand that if we have an intensive property, it's treated differently than an extensive property. Remember that extensive properties are properties that depend upon the quantity that we have. Intensive properties do not. If we have an extensive property, then we can actually add together directly the properties of the various components. On the other hand, if we have an intensive property, then everything has to be either mass weighted or molar weighted based on the molar mass fractions of the components of that mixture. So in general, the rule is this. And let's just start with extensive properties. Okay. With extensive properties, and I'm just going to use internal energy as an example, but this is also going to apply to the enthalpy, to the entropy, to the total volume. The internal energy of the mixture is just going to be the sum of the internal energy of each component of the mixture. Okay. Now, we should also recognize that the total internal energy, capital letter U, is just the mass times the specific internal energy. So we could also just plug that into this equation. So this is going to be the mass of component I, and then multiplied by the specific internal energy of component I, and then summed over all the components. Okay? So this is the equation that we generally use. Now I will note that there is some ideal gas data in your textbook that is on a molar basis. We might also just recognize that when we sum together the internal energy of each component, the internal energy of each component can also be thought of as the mole number N of that component, and then multiplied by the molar specific internal energy of that particular component. So it really just depends upon what kind of data we have from our reference material. If our internal energy data, or again, this will apply to enthalpy, volume, everything, and entropy as well. It depends on what kind of data we have, right? Look at the data, look at the units, and then either apply your mole number or your mass number as is appropriate. And again, I'll note that this also applies to enthalpy, it applies to volume, it applies to the total entropy as well. So this is what we do if we have extensive properties. However, it might be noted that for most problems, it's not extensive properties, it's intensive properties that we utilize, right? So if we have intensive properties, like specific volume or specific enthalpy or specific internal energy or the others, then everything has to be weighted based upon the fraction of that particular component. So let me do this again, but again, I'll just do it for specific internal energy, but we'll note that this also applies to those other properties. So we would note that the internal energy, that is specific internal energy of a mixture, is just going to be the sum over each component of not the specific internal energy of each component, but the mass fraction of that component multiplied by the specific internal energy of that particular component. So this is the equation that we would generally use when we have a need for specific internal energy data for a mixture, or again, enthalpy, entropy, and the others. I might want to note similarly that, again, some of our data is going to be on a per unit mole basis, and if that's the case, we still have to do a summation, but we're going to now sum based on the mole fractions, right? So this is going to be the mole fraction of component I, and then multiplied by the molar specific internal energy of that particular component. So either equation that you want to use is certainly appropriate. It just depends upon what kind of data you have available to you. Now, again, I would note that this applies to not just the specific internal energy, but it also applies to specific volume, it applies to enthalpy, it applies to entropy. Let's also note further that when we are dealing with ideal gas problems, as we will continue, we are generally going to assume that we have an ideal gas with constant specific heats, and as such, specific heat properties, since they are intensive properties, that would also appear on this particular list. So if we need data for CP and CV, which we often will, then we need to make sure that we use the right equation. Again, we take the mass fraction times the value of that specific heat number. So let me go through another example problem. And this example problem is somewhat more challenging than what we dealt with previously, because this one is an actual first law problem. So we're going to use the information that we've previously used plus more. So let me put our next example up here. Okay. So here's a new example problem, and as we're looking at this example problem, let me again note that This is from actually a previous edition of your textbook. This is 13 to 55, but this is from edition 7 of your book. Anyway, this particular problem, let me read it to you. It says that we have a mixture of gases, and it consists of 30% hydrogen, 40% helium, and 30% nitrogen by volume. Remember that volume fractions are the same as molar fractions for ideal gas mixtures. So when they tell you that this is a volume percentage, it's also the molar percentage. It says this mixture is expanded isentropically from 5,000 kilopascals, 600 Celsius, down to 200 kilopascals. And we want to calculate the work produced per unit mass of the mixture. Okay. So first I would note in a problem like this one, again, this is 13.55, the 7th edition. I would note in a problem like this one, this is a first law problem. I mean, if we're trying to find the work, we have to solve the first law. Now here I have a little bit of a problem with the problem statement. We can expand something isentropically either in a closed or an open system, right? We can expand, let's say, in some sort of a piston cylinder device, which would be a closed system as the system expands, or we can expand as this gas moves through a turbine. The author is not specific here, so I'm just going to have to assume one or the other. So I'll just solve this as if it were a turbine problem. So assume that it's a turbine, and keep in mind that means it's a single stream steady flow process where work is being produced by this particular turbine. Now, for most problems of this type, we would have to recognize that the first law should be, let's say, simplified in many ways. We have no information about the velocity in or out of this particular turbine, so we have to assume there's no kinetic energy change. We have no information about the geometry, that is the height of the turbine, so we would have to assume that there's no potential energy change. It does tell us that it expands isentropically, so we know that isentropic means that it's adiabatic reversible, so there's no heat transfer as well. So let's just make sure that we make those assumptions. We assume there's no kinetic energy change. We assume there's no potential energy change. We also know that isentropic is the same thing as adiabatic reversible, which really means to us that there's no heat transfer. So what's the first law for a single stream steady flow process reduced down to? Not much. The work is just equal to the change in enthalpy. So if we have a turbine where 1 is at the input, 2 is at the exit, and here is my turbine, basically I would just note that the work output, and we're trying to find work per unit mass, this is just going to be the enthalpy change, right? H1 minus H2, nothing more complicated than that. Additionally, let's keep in mind that as we're solving these problems involving gas mixtures, we're always going to assume that these are ideal gas mixtures with constant specific heats. So we know that the enthalpy change actually is the Cp, that is specific heat at constant pressure, times the temperature change. So in order to find the work, we really need two things. One thing is we need the exiting temperature, T2, and the other is we need to find Cp. And because it's a mixture, it really makes sense to put a little m here, just so we remind ourselves that it's a mixture that we're dealing with. Okay. So the question then is, how do we find Cp for the mixture? How do we find the temperature for the mixture? So, first things first, let's just talk about the problem statement. If we have an isentropic process and we have an ideal gas with constant specific heats, then we know that there are certain relationships that apply. One is that the temperature ratio is going to equal the pressure ratio raised to the k minus 1 over k power. And in fact, since the highest pressure is the inlet to the turbine, I would just tend to raise both these to the minus 1. In other words, we're just going to invert. So temperature ratio T1 over T2 is a pressure ratio P1 over P2 raised to the K minus 1 over K. This just guarantees that these numbers are going to be, positive numbers greater than 1. They don't have to be. They could be a fraction, but this is a little bit easier. So this is the equation we're going to have to solve. Now, we do know some of this information, right? We know the inlet temperature, we know the inlet pressure, and we know the exit pressure. We're trying to find T2. After all, that's what we need for this particular problem. Now, again, this is for the mixture, so it doesn't hurt to just put a little m down here, just to remind us that it's a mixture we're dealing with. Next, I would note that we need K, right? I mean, how can you solve this equation unless you have K? So how do we find K? Well, remember, K is called the ratio of specific heats. So we need to find Cp and Cv for the mixture so we could then find the ratio of specific heats. All right, so that's not too hard to do, but we do have to remember the appropriate equation. We remember that for a mixture, we're going to sum, for all these intensive properties like specific heats, we're going to sum using the mass fractions and then multiplied by the specific heats of each component I. So that's the first thing we're going to have to do. We need to find Cp for the mixture before we can find K. However, we also need Cv for the mixture. Now, you may, or perhaps may not recall, that the gas constant R is just the difference between Cp and Cv, again for this particular mixture. So in order for us to find Cv for the mixture, we really have two choices. We can either use the same equation. We can use Cv for the mixture as a sum of the mass fractions times Cv, or an alternative to this is to find R for the mixture and then simply find Cv by subtracting R from Cp. That's a little bit easier because, quite frankly, for a mixture, the gas constant is just going to be the universal gas constant divided by the molar mass of the mixture. And we are able to find the molar mass of the mixture, so I'm just going to solve it this way. I'm not going to bother to sum over all the components to find Cv. All right, so we can find R, we can find Cp, we can find Cv. That gives me the ability to find K. I already know the equation we need in order to find the temperature, and that would then be all I would need. I can then solve this particular problem. So the hard part of the problem is really the conceptual part, right? Just trying to make sure we understand which equations to use, which are appropriate. Now, one other thing I should note, since I do need the molar mass, I'm going to have to use the given mass information, the given molar information to find the mole fractions, to find the mass fractions, and utilize this to find the molar mass of the mixture. Recall also that the molar mass for the mixture is just the mass of the mixture, and then divided by the number of moles of the mixture. So that's really the first thing we got to do. We have to find the molar mass of the mixture, then we can find the gas constant, then we can find Cv and Cp, and thus K, and then T2, and then ultimately back to the top, and we can find our work term. Okay. Now, they don't give me the actual number of moles. They only give me volume percentages. We do recall, based on what was discussed at the very beginning, that the volume percents are going to equal molar percents. So we use a device here to solve these problems. Since everything is on a percentage basis, why don't we just assume that we have a total of 100 kilomoles of mixture. Now, there are some problems that are similar to this where you would be given percentages or fractions on a mass basis. If that was the case, then I certainly wouldn't say that the volume percentage equals the molar percentage, but you could use a similar device in that we can assume that we have 100 kilograms of material, and then those percentages can be converted into actual mass numbers so that we can use that to find the mass fractions or perhaps the mole fractions. So in this case, since we understand that volume and molar percentages are the same, the volume percentages are the mole percentages, I'm just going to assume that we have 100 kilomoles of material. And with that in mind, we can then find the mass associated with each component. So we would note then that the mass of a hydrogen is just going to be the number of moles times the molar mass of the hydrogen. If we assume a total of 100 moles of mixture, and we're told that 30% is hydrogen, that means we have 30 kilomoles of hydrogen. And then the molar mass of hydrogen has to be looked up in table A1. So this is 2.0 kilograms per kilomole, and this is just going to give me 60 kilograms. Similarly, we would find the mass of our other two components. So we have our helium gas, Again, N times molar mass of helium. So here we're told that we have 40% helium, in other words, 40 parts out of 100, so 40 kilomoles of helium. The molar mass for helium is 4.0 kilograms per kilomole, so that's going to give me 160 kilograms. And lastly, we would have our nitrogen gas. So that's the number of moles times the molar mass of the nitrogen. So again, 30% means 30 moles, so 30 kilomoles. And then the molar mass of nitrogen is just 28.0 kilograms per kilomole. So clearly we have a whole lot more nitrogen than anything else. We have 840 kilograms. And now that we have this information, now we can just take this and we can find the total mass. We can then find the mass fraction and continue on with the problem. All right, so total mass of the mixture is just the sum of the mass of each component. Just add the three numbers that are above, and we have 1,060 kilograms. Now that we have that, we can find our mass fractions. So the mass fraction of the hydrogen is just the mass divided by the mass of the mixture. So just take the two numbers that are above, and we get 0.0566. Similarly, we would find the mass fraction of the helium as just the helium mass over the mixture mass. So again, just take the two numbers from above, and we get 0.1509 as its mass fraction. And then lastly, the mass fraction of our nitrogen gas. Again, we just divide 840 into 1,060, and we get 0.7925 as the mass fraction of the nitrogen. So now that we have all those mass fractions, we can continue. Why don't we find the molar mass first? The molar mass is just going to be the mass over the number of moles of the mixture. So what is that, 1,060 kilograms out of 100 moles. And this is then just going to give you, what, pardon me, 10.6 kilograms per kilomole. So this is the molar mass of the mixture. So that's one thing we're going to need. We can now use this to find the gas constant. So the gas constant is just the universal gas constant divided by the molar mass of the mixture. So we'll use the same numbers we've used previously, 8.314 kilojoules per kilogram, do it again, kilojoules per kilomole per Kelvin, and then divided by 10.6 kilograms per kilomole. And we go through our math here, and we get the gas constant of the mixture of 0.7843. That's going to be kilojoules per kilogram per Kelvin. All right, so there's our gas constant. Now let's find Cp for the mixture. So again, this is just going to be the sum of our mass fractions times Cp for each individual component. So let's just do that then. So for the hydrogen, we have 0.0566, and then Cp, well, this is data that's again going to have to come out of our tables. So you can get this data in table A2. So in table A2, by the way, I'm using table A2 part A. Basically, this is the room temperature data. Now granted, in this problem, the temperature is quite a bit higher than room temperature, but the fact is table A2 part B only lists 6 different gases, and helium is not one of them. So it makes no sense for me to try to estimate the average temperature for nitrogen and hydrogen and then use that data and then finish the problem and then check to see if I made a good assumption. I have to go back and redo the problem if my average temperature assumption wasn't so good. I'm just going to assume that everything is at room temperature, and this is going to give me a number that's certainly close enough. So we have 0.0566. Cp is 14.307 kilojoules per kilogram per Kelvin. And then we add to that the same information for the helium. So 0.1509. And for helium, we have 5.1926 kilojoules per kilogram per Kelvin. And then we add to that our information associated with the nitrogen gas, so 0.7925. And then specific heat at constant pressure for nitrogen is 1.039 kilojoules per kilogram per Kelvin. And we just add all the numbers together now. We get 2.417 kilojoules per kilogram per Kelvin. Okay. So now we have Cp for the mixture. Now we can find Cv. So R is Cp minus Cv for the mixture. Cv for the mixture is therefore Cp minus R. We could just take the numbers that are directly above and go through our mathematics, so we get a value of Cp of 1.633 kilojoules per kilogram per Kelvin. Okay. Now we have Cp and Cv, so now we can find the ratio of those specific heats, Cp over Cv of the mixture. So again, just plug in the two numbers that are directly above, and we get K of 1.480 as our ratio of specific heats. So that was a whole lot of work just to find K, but K is exactly what we needed. So now that we have K, now we can complete the problem. Remember once again that our temperature ratio is going to equal the pressure ratio raised to the K minus 1 over K power. So T1 is known to us. Certainly we're going to have to make sure that we convert from Celsius into Kelvin. So we add 273 to 600. So we get 873 Kelvin over T2. And then the pressure ratio, these are in units that are just fine, although we have to make sure they're both in kilopascals rather than one in kilo and one in megapascals. So basically 5 megapascals is 5,000 kilopascals, and 200 kilopascals is at the exit. Since K equals 1.48, then this is going to be 0.48 over 1.48. And there's only a single unknown here. We can calculate T2, and we get 307 Kelvin. And then, having this temperature, we're almost done. Now we can find the work as just Cp for the mixture multiplied by the temperature change. T1 minus T2. So again, it's just a matter of plugging in the numbers we already have, 2.417 kilojoules per kilogram per Kelvin. Both our temperatures are in Kelvin, so we can just take the difference between the two. So 873 minus 307. By the way, if these temperatures were in Celsius, that's fine. The temperature difference in Celsius is exactly the same as the temperature difference in Kelvin. You know, 1 unit of Kelvin is the same as 1 unit of Celsius. They're the same scale, they just have a different 0 point. So we go through our math, and we get 1,368 kilojoules per kilogram, and that then is the final example problem they don't want to show for this material. Now, let me just make one final comment here. If this problem was a closed system, and we were finding the work for a closed system, well, then that work is based on the internal energy change, not the enthalpy change. And of course, an internal energy change is Cv for the mixture times T1 minus T2. So we would have to do everything we did previously. Nothing is different at all, except for our final step here, where we would have to use Cv times the temperature difference instead of Cp. That gives us our internal energy, or our work, associated with a closed system. So now we move on. So now that we have all the basics associated with mixtures, now we're going to move on and begin looking at one very special mixture, which is basically our atmospheric air. I'm sure we're all aware that atmospheric air is not just air, right? It's air which contains oxygen and nitrogen, and then, trace amounts of various other gases, pollutants, carbon dioxide, noble gases, argon, xenon, et cetera, et cetera. That's the air component, but there's also water vapor. So when we talk about atmospheric air, we're really talking about air-water vapor mixtures. This is an extremely important part of thermodynamics. There are so many processes that involve air-water vapor mixtures that we really need to spend a significant amount of time dealing with this. So this is our next topic, air-water vapor mixtures. Okay. Now certainly the information that we've learned previously is going to apply here. We will note that these air-water vapor mixtures, that is the atmospheric air, actually contains, or is assumed to contain, two components. Okay. One of those components we're just going to call dry air. Okay? And the dry air is everything that's not water vapor. It's the nitrogen, it's the oxygen, it's the trace amounts of all those other gases. That's all considered part of dry air. And clearly that's a multi-component mixture. We wouldn't want to have to calculate that directly in every single problem. Fortunately, we don't have to. I'm sure you've seen in the tables in the book that there are many listings for air data. When it says air, it's the dry air that already has calculated, or I say where we have already calculated the mixture properties for us. The air data in your tables would be dry air data with an apparent molar mass, an apparent gas constant. All of that is already going to be presented to you. So we're not going to have to calculate any more data for dry air. The dry air is simply going to be there. The other component is our water vapor. Okay. So we're going to treat the dry air as if it were a single component. And again, it's going to have its own values of molar mass, gas constant, Cp, Cv, and all of that. Also, I might note that the atmospheric air that we're going to deal with is generally at a very modest pressure. Atmospheric pressure, 101 kilopascals, give or take a little bit depending on our elevation. The temperature of atmospheric air is also going to be in a relatively tight range, maybe from minus 20 or 30 Celsius up to perhaps 40 or 50 degrees Celsius. Given this information, we're going to treat the atmospheric air as an ideal gas with constant specific heats but at room temperature. Okay, so we're going to treat it in a very simple fashion. We're not going to deal with any variations in specific heat or temperature. We're just going to take data for room temperature data. We're just going to take data for air at room temperature. Okay. Now, let's start looking at some of the equations that are associated with these types of problems. First, we would recognize that the pressure of the atmospheric air, which we might just call the pressure of the mixture, right? In fact, why don't we just call it P? This is going to be the sum of the partial pressures of each component. Okay? Now, in this particular subject, it's just two components, right? So we're just going to write it this way. We're going to say that the total pressure, or if you will, the mixture pressure, the atmospheric air pressure, is just the sum of the pressure of the dry air plus the partial pressure of the water vapor. Now remember again, these are partial pressures, okay? These are the pressures that you would have if those components existed alone in the volume of our atmosphere, okay? Clearly, if the water vapor existed alone in the atmosphere, it would have a much lower pressure than if it exists as it really does as a mixture. But nonetheless, the pressure is going to be the sum of the pressure of each component. PA represents the partial pressure of the dry air, and PV represents the partial pressure of the water vapor. Okay, so A for dry air, V for water vapor. This is basically just Dalton's law, right? And then with regards to some terms of interest to us, again, we're not just interested in these thermodynamic properties because it's fun to look at. I mean, we're looking at real problems. And when we're talking about problems involving atmospheric air, there's a couple terms that are really of interest to us. One of these is called the specific humidity, and the other is called the relative humidity. Now, quite frankly, relative humidity is something that you hear about all the time, right? You watch the weather report, it tells you what the relative humidity is. The relative humidity is not a measure of the actual humidity. It's a measure of the humidity compared to the maximum amount that the atmosphere could hold at that particular temperature. The specific humidity is what we are really interested in this class, because this is going to give us the relationship between the amount of water vapor and the amount of dry air in any atmospheric mixture. So with this in mind, there are two terms of interest. Okay? One we would call the specific humidity. And by the way, you could see in various textbooks that this has a couple of other names. Sometimes it's called the absolute humidity. Sometimes it's also called the humidity ratio. Personally, I like the word humidity ratio, but it's all the same, okay? And the other term of interest is our relative humidity. So these are of interest to us. We're interested in the comfort level of air, right? We know that if the air is moist, if there's a large water vapor component, then the air is very uncomfortable. We also know that if air is dry, it's also very uncomfortable, right? If there's not enough moisture in the air, it's uncomfortable. Some people get nosebleeds if the air is too dry. So this is of interest to us, right? It's of interest to us because we're going to be solving problems that would allow us to analyze the comfort level of air. I mean, ultimately, we're going to use this information to solve air conditioning types of problems. You know, you'll have air at certain conditions, and you'll need to do something to that air, adding or removing heat, adding or removing water vapor, so that the air becomes comfortable for us to sit in. So let's begin by looking at specific humidity. And first, a definition. So here we're going to use a Greek letter omega, and that's defined as our specific humidity, and this is the mass of the water vapor divided by the mass of the dry air. So that's of interest to us. We would just write it this way, mv over ma. Okay. Now, we're still dealing with a mixture, although it's a mixture of ideal gases with constant specific heats. So let's just modify this equation a little bit. Let's just keep in mind that from our ideal gas relationship, and I'll just write it in this form, PV over RT is going to equal the mass, and this is going to apply to each of the two components. So let's find this for both the water vapor and for the dry air, and let's place it into the equation for the humidity. So omega equals, now what would be the mass of the water vapor? Well, this is just PV times the volume of the water vapor over the gas constant over the temperature of the water vapor, and then for the dry air it's PA over the volume of the air divided by the gas constant of the dry air and then the temperature of the dry air. Okay. Now, let us please keep in mind that PV and PA are the partial pressures, right? This equation applies to each component of a gas, but it would apply with the partial pressures. Now, let's note, please, that in the atmosphere, the volume of the atmosphere is the same whether we're talking about the water vapor or the dry air. So these two volume terms are going to cancel out. Also, in the atmosphere, the temperature is the same for the dry air and the water vapor, right? There's no difference between them. The two gases are homogeneously mixed. So the temperatures are the same, so they're going to cancel out of the equation. So this equation for the humidity ratio then just becomes the partial pressure of the water vapor over the partial pressure of the air, then multiplied by the gas constant of the air over the gas constant for the water vapor. Now, we can look up these gas constants in our tables, right? We can go into table A1, and we can get the appropriate data. So PV over PA, and then the gas constants for air is 0.287 kilojoules per kilogram per Kelvin, and the gas constant for water vapor is 0.4615 kilojoules per kilogram per Kelvin. You see the units cancel out appropriately, and if we go through our mathematics, then we get this equation that omega is equal to 0.622, and then multiplied by PV over PA. Or we would just recognize that PA plus PV is equal to the total pressure, or in other words, PA is just the total pressure minus the partial pressure of the water vapor. So that can be substituted into the denominator, and then the numerator just remains the same, 0.622, and then multiplied by the partial pressure of the water vapor. Okay. So this is an equation that we're going to use a lot. I'm going to call this one equation A, and we will get back to it at a future time. And that's all the time I have for today's lecture, so we are now finished. And thank you very much.